This is lecture 11. So, the motivation of today's lecture is to round up S parameters, transmission lines, and then move on to something which is more circuity. Right. So, up until now, I have been talking about why should we be comfortable in analyzing transmission lines, uh, and what happens if we do not take the transmission line, the delays associated with the transmission line into account. What I today, in the next few minutes, what I would like to do is to concentrate on a slightly different aspect, right? Without getting too much technical into the maths of it. Uh, Hopefully, you'll be able to appreciate what are the impacts an actual transmission line can have if we do not take care of it in an actual design. Okay. So let me take the example of an amplifier. Let's say I have an amplifier. Let's take the example of a common source amplifier. Okay. And let's say I'm not showing the biasing here. This is, let's say, the incremental picture. Normally, we take the output for the common source amplifier from the drain. But let's say uh, this common source amplifier is sitting inside the chip, and uh, I have a long uh, output cable which runs all the way. It's a very long output cable, right? And probably the output is a capacitor. Okay. So now, what do you think can happen in this regard? So, in order to make the analysis a bit more ideal, what I would like to do is say that, let's say this is the current source, and let's say biasing is taken care. Do not bother about biasing right now, right? We understand that biasing has to be done, and it has been taken care, right? So let's assume this is the current source, and I have an incremental input that has been applied, and everything is biased, and so on and so on. Okay. And let's say you have done your simulations. You have this is your chip boundary, right? And you have done your simulations, and you know that in your simulation test bench, say this is my let's say I have done this simulation test bench. This is my simulation test bench, and I did not take into account the long delay line, right? And this works perfectly fine. But now I fabricated the chip in order to test whether things are fine or not. I connected it to a long delay line. I wanted to connect it to a capacitor. Capacitor now sits on the board, right? But naturally, the chip and the capacitor will not be sitting just next to each other. There will be some routing, and that this long delay line essentially it mimics the routing. Okay. So now, from whatever we understand, what do you think can happen? So, given a certain frequency, you can obviously see that uh, there will be some resistance, parasitic resistance associated also. So, what can happen? You will have some forward going wave. So, it will go and hit there, and then it will come back, and you are going to get a reverse, a reflected wave. Now, depending upon whether what the length of the line is and what is the frequency of interest, this V plus and V minus can constructively interfere, and you can have really large swings here, right? So you are probably anticipating some swings which is of the order of the voltage supply or less than the voltage supply, but because of this constructive interference, you can end up having really large swings. And in the worst case, what can happen is that this can end up breaking transistor itself, right? If you are not careful, right? So this is one possible scenario where you might end up getting you might end up getting reliability concerns. This typically can happen in power amplifiers. We'll talk about this in a bit more detail at the back end of the course when we talk about power amplifiers, right? So another thing that can happen if you are not careful is the following. So let's say I'm an analog circuit designer. I am trying to design a unity gain buffer, and I know that I have an off-chip capacitance that I need to drive. Okay, so I have a capacitor here. I need to drive. Again, let's say this is the chip boundary. Okay, so I know that an unity gain buffer is nothing but this. Right, so I have connected it like this. This is supposed to work. Now, by the way, this is a voltage control current source. This is a GM, or rather, I should define it properly. This is a voltage control current source, and the definition is if there is an input V1, V2 between the plus and the minus terminals, then the output current is GM times V1 minus V2. Okay. I mean, you can assume that this is this basically is a representation of this, where this is V1, this is V2, and this terminal is not accessible. The other terminal is grounded. Uh, so these two are equivalent. Okay, fine. So this is the first order circuit. This should be unconditionally stable, and I should be happy. But now, what happens is if there is a transmission line here, so this is effectively giving me some delay. Now let's see what happens. So this is V naught. This is V naught. Instead of doing the brute force analysis, what I will do is I will try to find out the try to find out the loop gain and see if from the loop gain if I can figure out whether things are stable or not. Okay. Okay. So let's do that. Let me make it even more simpler. I do not want capacitor. Let's say uh, say this is supposed to be an resistor. Okay. And just to make the point, a resistor is sufficient. Capacitor, there will be some frequency dependent uh, components. We can still do the analysis, but this, for the sake of brevity and to make the point, let's replace this capacitor with the resistor. Okay, so if I want to do a loop gain analysis, again, so what should I do? So in order to do a loop gain analysis, first is we need to break the loop. Again, a quick refresher of a loop gain. So let's say I had from a control theory perspectives, let's say we had feedback loop. This is Vi, which is V naught. So I know V naught by Vi is G by 1 plus Gh. And what is loop gain? Loop gain is Gh. How do I find loop gain? In order to find the loop gain, I need to break the loop somewhere. Let's say I break the loop here. I break the loop there and I get and apply a test voltage. And I desensitize the input. That is also an important part. Right? I desensitize the input and see what comes back. Right? In a very heuristic sense, let's see what comes back. So this is G times V test. This is GH times V test. So this is minus GH times V test. So the fact that this is minus is basically telling us I have negative feedback, and whatever comes back, mod of that is the loop gain, right? So loop gain is essentially, or rather negative of that is the loop gain. The loop gain is GH, and all we have to ensure is that if the loop is stable, so for a stable loop, in the Nyquist plot of GH, there must not be a clockwise encirclement of the -1 0 point, right? So this is again a refresher. This is a refresher of your Nyquist criteria from our undergraduate days. We are going to do, right. So let's see. So let's say we have this loop, we have this long delay, and we have this R, right? We short the input, desensitize a voltage source means shorting it. We apply, so the loop is here. So I break the loop here, apply a test voltage here, and this is GM, which means that the current that is coming out is GM times V test. Okay. Now, this is the transmission line, and whatever is the current that is coming out, right? Uh, Note that this is a source, right? If now the current waveform, right? So essentially the if you think of it in this way, if this direction of current is minus GM times V test, so this is the incident current, right? And no current can flow into a voltage control current source, right? So the current that, so essentially the impedance here is infinite. Impedance looking into this is infinite. The doubt is infinite. So the total current is essentially the current that is launched, right? So that current is going to move forward. So minus GM times V test current is going to move forward, and it after some time tau d, it is going to appear at the other side. Okay. So the current that is going to appear here is essentially in frequency domain is minus GM times V test e to the power minus j omega tau, where tau is the delay associated with the line, and this goes into R, and it is going to create a voltage times R, right? So this is essentially this voltage is V return. So what is your loop gain? Loop gain is negative of whatever is V return over V test. So that is GM times e to the power minus j omega tau times R. So GM R times e power minus j omega tau. Okay. So quickly, what is the Nyquist plot of this? So I am plotting the real of loop gain, real GH. So this is GH versus imaginary GH as frequency goes from 0 to infinity, right? And this is your -1 0 point. So at omega equal to 0, what is your loop gain? It's totally real GMR, and let's say GMR is more than 1, right? Because I mean, you ultimately would want the, if for unity gain feedback, right? You would want the loop gain to be much greater than 1. So GM has to be much greater than 1. GMR has to be much greater than 1. GMR is much greater than 1. So GMR is probably somewhere here, not to scale. And then as frequency increases, what is happening to the phase? You're saying it's an encirclement, right? So what happens to the phase? The phase reduces, right? The phase is essentially minor. phase is essentially minus omega tau. So as frequency increases, right, your phase decreases, and so essentially phase, and what is the representation of phase? Phase is essentially this angle, right? So, and as you can see, this with as frequency increases, this will basically go on encircling, and it will keep on encircling for infinite number of times. But the key thing is that it's a clockwise encirclement of the -10 point, right? So essentially this becomes unstable. The loop is unstable, right? So as you can see, a simple we started off designing a simple buffer, uh, a voltage control current source driving a resistor, put in a loop. Nothing is simpler than that, right? Uh, Nothing. I mean, no feedback loops is supposed to be simpler than that. But just because you have a transmission line in between which gives you delay, your entire thing can become unstable. So there are ways of making it stable. I will not get into detail of that, but intuitively you should be able to understand. So if you have to make it stable, you have to ensure that this guy does not encircle -10 point, which means the magnitude has to drop as frequency increases, right? And how do you ensure the magnitude drops? You'll have to put some capacitor at various points so as to ensure that the magnitude drops and you kind of get some amount of stability, right? But I mean, those things have to be done carefully, otherwise you will end up with other problems. But this is not a part, this is not a class, or this lecture is not about how to make feedback loop stable, but this is just to motivate you with the fact that if there are transmission lines, if there are long lines having significant amount of delays, and you are not careful, then you can potentially have issues with it, right? So the issues, to summarize, were from the perspective of a receiver. The issues where you can end up having intersymbol interference, right? Because if there are multiple, if the signals are coming in and they're reflecting, and the next signal is coming in again, they're reflecting and they're interfering, then you might end up seeing intersymbol interference, and you might have you will lose signal integrity and signal fidelity. If you are doing a transmitter, for example, then there can be possibility of the reflections having landing on top of the incident wave, and you can have large amplitudes, right? And this is significant in a transmitter, because in a transmitter you are already sending out large signals. In a receiver, typically you are receiving very weak signals, feeble signals, but in a transmitter you are shouting at the top of your voice, and if the echo also comes back and increases the amplitude, then it can break the device. And a third thing that we saw is that if there is a feedback loop and you have delays due to transmission line in a feedback loop, it can also lead to instability. More we'll talk about more formal ways of dealing with this stability analysis using S parameters when we talk about power amplifiers later on in the course. Okay, so now enough of analysis. Now let's get back to some amount of design. I'm sure you guys are bored of these S parameters and B plus and B minus. This is a design course, so we should also go back to some amount of design. Okay, so let's go back to our receiver. So our receiver is again an antenna, a long transmission line. I'm not including the SAW filter, but we understand we need an amplifier, right? We need an LNA. So if I limit myself to a single transistor topology, right, what are the ways I can design an amplifier? So clearly a common source amplifier is the most common and popular amplifier, but clearly this common source amplifier is of no use in this context, because of what? Because its input impedance is not matched, right? So not matched. Ideally the common source amplifier should have infinite impedance, but in reality it has a capacitance, right? It has a capacitance CGS, it also has a capacitance CGD, right? And because of that, you are going to have reflections. There is no real part, so you are going to have a if I mean there can be real part if I include CGD, but we'll talk about that not for in today's class. But you get the idea that if you have a common source amplifier, you are seeing only a capacitive impedance, and this is not going to help in matching. Okay, so what else can I do? Okay, so I can simply say that I have a transmission line. By the way, I mean from now on I am not going to use this antenna. I'll just assume that I have a receiver. I have a voltage source with a 50 ohm load, right? This is my antenna. Okay, so if I still want to use a common source amplifier and I want matching, what should I do? Then I can probably put an explicit resistor R, which is equal to 50 ohm. This Z naught also is equal to 50 ohm, and it has some delay tau, and there is some capacitance CGS, right? So what about the matching? What is the reflection coefficient of this at this interface? What is the gamma? So gamma here is nothing but uh, R parallel 1 by j omega CGS minus R by R parallel 1 by j omega CGS plus R, which is essentially by 1 plus j omega R CGS minus R. Okay, so I get R's cancel. Okay, so I get, so this has a obviously these are the real part and this has an imaginary part. I get certain amount of, if I split it up into real and imaginary, what do I get? Equal to, okay, so this is the real part, and this is the imaginary part. So clearly you see that at low frequencies, right, at omega much less than 2 by R CGS, right, your gamma becomes approximately omega square R square CGS squared minus j 2 omega R CGS, and clearly your as at low frequencies, right, your when omega R CGS is much lesser than 1, right, then gamma tends to 0 and you are going to have a, okay, so this is one way of biasing your network, one way of ensuring that you do not have any reflections. Okay, so that's good. What about what are the topologies of single transistor networks that we have. By the way, before we move on, let's complete the loop here. Let's complete the discussion. Right. So this is Vi and that is Rd, and this is inside the chip. This is inside the chip. So assuming things are matched, right? Assuming omega CGS R is much less than 1, right? I matched. Then what is the voltage at this node? What is the voltage at this node? So clearly the voltage, there is no reflection if it is matched. Obviously, if there is a CGS, there will be some reflection, but we are neglecting the reflection because we are operating at a frequency which is much honors this inequality. So this voltage forward going wave is Vi by 2, and essentially we are going to get Vi by 2 at the input of the common source amplifier also, right? We are going to get Vi by 2 at a, but with some delay, right? So I am not showing the delay here, but if I am only interested in the mod, so I am going to take mod Vi by 2. Okay. So what is the current that is going to that it is going to introduce? So this current will be Gm times Vi by 2, right? And what is the voltage at the output? This voltage at the output is Gm times Vi by 2 times Rd, right? So what is the so-called voltage gain? So V naught over Vi is Gm Rd by 2. But again, note that even though this is V naught over Vi, this is typically not what we call it as gain in RF parlance. Gain is with respect to a matched interface when with respect to the signal that is going in, right? So gain is essentially, typically your gain is with respect to Vi by 2. So essentially V naught over Vi by 2, right? Essentially Gm. So if you find an RF interface saying that I have a gain of this much, which essentially means that it is they are claiming that it's a gain with respect to a matched interface. So the gain is GMRD. Okay, so this is one way of biasing. Fine. So what is another way of biasing? So I am not going to criticize any of the biasing schemes right now. Rather, I am not going to criticize any of the matching schemes right now. Right now, the goal is to understand what are the ways of matching, and later on we are going to see what are the pros and cons of each of these matching schemes. Okay, or at least some of their matching schemes. So let's what other way of matching is there? So again, this I cannot do anything. This is there. Common source amplifier, we are done, right? What other transistor topologies are we familiar with? What about a common drain amplifier? Firstly, common drain amplifier is not an amplifier, right? So you do not get any amplification out of a common drain amplifier. So let's keep that away. What other things that I know about? I know about common gate amplifier, right? Let's see common gate amplifier. In common gate amplifier, the output basically goes to the input goes to the source, right? This goes to the source. This is incrementally grounded. The gate is incrementally grounded. And you have probably some resistance Rd. Okay. Now, what is the so clearly the resistance here is not fully capacitive. So, what is the impedance looking up? Rin is essentially the zeroth order approximation is 1 over GM, right, where GM is this is neglecting channel length modulation in the transistor. Let me call this in 1. Okay. So if I want to match, right, if I want to ensure things are matched, what should I do? I have to ensure that for matching, ensure Rn is equal to R equal to 50 ohm, i.e. Gm equal to 1 over 50 ohm, which is 20 millisiemens, right? So you have to size your transistor in such a way that, and you have to bias your transistor in such a way that your it has a GM of 20 millisiemens, and you connect it in the incremental model in the way that we show here, and you are going to get a match, right? But there is just like anything else, neglecting channel length modulation is probably not necessarily always a always a acceptable solution. But if I neglect channel length modulation, this is what we are going to get. If I do not neglect channel length modulation, then what happens? So as it turns out, I'll just sketch this part now. So in the presence of channel length modulation, that is, I have a GDS, right? What is the input impedance? Rin. So how do I know? So how do I go about figuring out the input impedance? I apply a test voltage V test, and there will be a current I test. I have to find out I test in terms of V test, and basically V test over I test is essentially my input impedance. So I know that this I test comes out on the other side. It has to, and goes to RD. It is going to create a voltage I test time RD here, right? So if I do a KCL at this node, what do I get? So I know that this current that is going through the transistor is GM times V test, right? Okay. So I know that then GM times V test plus the current through the GDS. The current through the GDS is nothing but V test minus I test times RD times GDS. This is equal to I test, right? So this is KCL at drain. So which essentially means that I collect the terms. V test, this is GM plus GDS equals I test 1 plus GDS times RD, which means that your V test by I test is approximately equal to, if I assume GM is much greater than GDS, right, is 1 plus GDS RD over GM. The assumption is GM is much greater than GDS, which is a fair enough assumption, because if GM over GDS is not more than unity, then you don't have an amplifier in the first place, right? So which essentially means that your Rin is equal to 1 over GM plus an extra term, which is RD by GM over GDS, right? And what is the GM over GDS? It's basically the intrinsic gain of the transistor itself. So basically I can write your Rin to be equal to 1 over GM plus the load resistance RD by the intrinsic gain of the transistor. So this is a handy rule of thumb to remember. So this is important, so I'll just sketch it also. So in the presence of channel length modulation, a better approximation of Rin is 1 over Gm, which I am anyway supposed to get because I am looking into the source, but plus an additional term. The additional term is the whatever the load that is connected on the drain divided by the intrinsic gain of the transistor, right? So if I neglect GDS, then the intrinsic gain of the transistor is infinite, right? If JDS is 0 or RDS is infinite, the intrinsic gain of the transistor is infinite, then the effect of RD doesn't matter, right? The Rin is always 1 over Gm. But if you have a fair enough large value of RD, then the input resistance can also change, right? So and since we are talking about matching, where we have to be within a certain range of 50 ohm, so essentially this is important to take into account the effect of whatever it is connected at the drain side of your transistor, right? Given that whatever is connected to the drain side of the transistor can also have an impact. Okay, fine. So let's now again revisit. This is incrementally your Rin is 1 over Gm plus Rd by intrinsic gain of M1, right? And you make this to be is equal to R by design. You design your GM, you choose your RD and you choose your intrinsic gain in such a way that this is approximately equal to R. So you have matching. By the way, I have again neglected capacitance associated with that node because it's again connected to the source. There is a capacitance, there is CGS capacitance associated. But again, the assumption is the same, that we are operating at lower frequencies like in a common source amplifier. Okay. So, so this voltage here, if this is Vi, this voltage again will be Vi by 2. Delayed version of that, I am not considering the delay because we are assuming there is no reflection. So if this is Vi by 2, what is the current? And this is also Vi by 2. So what is the current that is going in under matched condition? The current is Vi by 2R, right? So this Vi by 2R current is going to flow in, and this Vi by 2R current is going to flow out through Rd also, and it is going to create a voltage at the output which is Vi by 2R times Rd, right? So again, what is the gain? So V naught is Vi by 2R times Rd. So your V naught over Vi by 2 is essentially Rd over R. So this is the gain that you are going to get using a common drain topology. Okay, and let's do one more. So now you might wonder that, okay, we are done with common source, we are done with common gate, common drain we don't want to do. What else is remaining? Actually, there are quite a few that is remaining, but I will show you one more popular configuration, and that is as follows. Now note that what are we looking for? We are essentially looking for in both these cases, so one final popular architecture that is often used for matching is the following. I mean, I'll give you a hint, and I'm pretty sure you'll be able to understand. So note that what are we trying to? If you see this topology, right? Assume that this GDS stuff is not there. Okay. So what are you trying to? How are you trying to synthesize the impedance? We're looking into the source, and looking into the source, the resistance is effectively 1 over Gm, and 1 over Gm gives us the required impedance for matching. Correct? So, what other ways can you have a transistor where you can get 1 over G? And one most easy way to, one of the most popular and used configuration is that of a diode connected transistor, right? So, again, let's say I have a diode connected transistor. What is the looking in impedance? 1 over Gm, right? So I can then obviously use this for matching, right? So I can use this and connect it here for matching. It will be matched, but the problem is that I will not be able to get any gain out of it. Only matching is not sufficient. If I am trying to make an amplifier, I would like to get a gain out of it. In the previous two configurations, we are getting a gain. Here, in this configuration, if Rd is greater than R, then we have gain, right? And the previous configuration, Gm times Rd, if it was greater than R, greater than 1, then we had gain. So similarly, here also we would like to have gain. So how do you get gain out of this configuration? Clearly, this is not enough. But if you recall, one of the topologies that we study in our undergraduate days is, let's say I have an op amp, right? And let's say I put it in an inverting configuration. I call this RF. This is R1, and let's say this is incrementally grounded. Then what is V0? You kind of get V0 to be equal to minus RF by R1, right? But this is under the assumption that this is virtual ground. Right? This is virtual ground. But in this case, in our case, right, firstly we don't have an op amp, right? And there is no virtual ground. But do we have something similar? We actually have something similar, right? Because instead of op amp, we have a voltage control current source. This is essentially a voltage control current source. I can, if I redraw this as this, right? So this kind of starts to look similar to the op amp picture, not exactly the same, but similar. So if I want to have gain, what should I do? Just like in case of an op amp, we can probably have something here with RF, correct? Okay. So what is the input impedance looking in here? So what I am basically asking is, what is the input impedance of this structure? Again, if I apply a V test, this is RF, right? So the current that goes in is Gm times V test, and this current essentially comes through this path. So your I test is essentially Gm times V test. So therefore Rin is 1 over Gm, correct? So if that is known, this looking in impedance Rin is 1 over Gm, and we make this equal to R, so then it is matched, right? If this is matched, then what is the voltage here? Like before, this is Vi by 2, right? If this is Vi by 2, and I know this current, what is the current that is coming out? That is Vi by 2R. So what is the current through RF? same Vi by 2R, then what is this voltage? This is Vi by 2 minus Vi by 2R times Rf. So I can also write it as Vi by 2, 1 minus Rf by R. So what is the gain? It is V naught over Vi by 2 is 1 minus Rf by R. Right? So if Rf by R is greater than, basically is Rf is greater than 2R, we have gain. Correct? Again, like before, we have neglected GDS, but if I don't neglect GDS, so you can do this yourself. I'll give you the answer. If I don't neglect GDS and if I simply do the incremental models, what is the looking in impedance? This looking, if you write out the KCL KVL, this Rin you will find to be approximately equal to 1 over Gm plus Rf divided by the intrinsic gain of M1, right? So M1, just like before. Okay. So now if you have to match, you have to ensure that you are matching with respect to this, right? So if you have to ensure that this is equal to R for matching. Okay. Okay. So before we stop, so what are the things that we in order to summarize today's lecture, what all things did we learn? We saw a couple of ways where not taking care of these long transmission lines can harm us, right? In terms of causing breakdown or in terms of causing stability issues in a feedback loop. Then we saw, then we started, once we understand the efficacy of matching, right? So from the receiver perspective, we tried to figure out ways of using single transistor circuits for to implement a match. We saw a example with a common source amplifier, how we can match. The common source amplifier intrinsically has a capacitive impedance, so that cannot be used for matching. So which means we need to put an explicit resistor R. Under certain conditions, of frequency, it will give you some match, decent match. And the second topology that we saw was that of a common gate amplifier, right? Where looking in impedance is essentially 1 over Gm. That is a very first order approximation. A better approximation is 1 over Gm plus the Rd that we have divided by the intrinsic gain of the transistor. In order to ensure a match, you have to ensure this Rin becomes effectively equal to R. And the third option that we saw was basically a transistor in negative feedback, right? It's diode connected transistor with a resistance plugged in, and this also gives you some gain, and it also gives you match. And all three topologies have their usage, and we will later on we'll not have the time to go through all three topologies, but we'll go through a couple of them and then see what are the pros and cons of each of them, right? So by the way, these are not, by no means these are the only three topologies. There are many other topologies which using which you can match. These are some of the popular topologies for which you can get a broadband match. When I say broadband, I mean for a wide range of frequencies. And and later on you will see that there are certain topologies which have their advantages with regards to getting a narrow band match, and that is something that we will be dealing with once we go into LNA design, after we have covered